Well, happy Sunday, students. This is Sunday, January 23rd, and today we are going to start working on moments and couples. And before we get started working problems, I want to do some definitions with you first. So that's what we're going to start off with, and then we're going to work quite a few problems, actually. Again, I hope you're doing well. Mr. Morris is hanging in there. So anyway, let's go ahead and get started. I'm going to share my screen with you here, or I'm going to use the overhead projector to present. Give me just a second here. So I hope you can see my paper okay. It looks like you can. So this is chapter 3 of your textbook. Okay, and it's on moments and couples. Moments and couples. Okay. Now, we need to do some definitions here, okay? So we're going to start off with a moment. A moment is defined as a force times, or multiplied rather, so times a perpendicular, hopefully I can fit that all in there, perpendicular, tight squeeze there, perpendicular. So a moment is defined as a force times a perpendicular arm. Okay. A moment is defined as a force times a perpendicular arm. Now, this word perpendicular means 90 degrees. It's very important that you understand that, okay? So I'm going to start off with a cantilever beam. Cantilever beam has one fixed end and one free end. All right, and let's say you want to take the moment about this point A. So we'll label that as point A. And let's say we have 100 pounds. This is a vector. So this is 100 pounds being applied to the very end of the cantilever beam. Again, let me go ahead and write this out so you understand. This is called a cantilever beam. It's simply supported at one end, and free is a free end here, okay? So one end is fixed. And let's say that it is 6 feet from point A. Now, if I were to ask you to calculate the moment about point A, knowing this information, the first thing you need to do is look at the force and see if the force is perpendicular to the beam, which it is. It is perpendicular, okay? So here's our equation. So the moment is equal to some force times a perpendicular distance, okay? All right, some books use lowercase letter d. We can do that if you want. It's just a force times a lowercase d. Force times a perpendicular distance, okay? Now, our force is 100 pounds. So the moment about A equals force is 100 times, sorry, I forgot to write the pounds in there, 100 pounds times 6 feet. All right. So that's going to equal what? 600 pound feet. 600 pound feet. Now, here's the thing about this problem. If you look at this point A and just imagine that being a pivot point and you're applying a force here, it's going to cause a clockwise rotation about point A. This force will cause a clockwise rotation about point A. So in statics, we call a clockwise rotation, we have to give it a negative sign. So when a force is causing clockwise rotation, okay, clockwise rotation is negative, all right, negative. And if it's a counterclockwise rotation, it is a positive, okay? So this 100 pounds times 6 feet is going clockwise, so it is negative. So it's negative, okay, negative 600 pound feet. But the way you actually write this would be the moment about A is equal to 600. You drop the negative sign and you show the direction with the arrow. So clockwise. Okay. All right. So let's look at another example. Let's take a door. Let's take a door. You know, the door has a hinge on it, right? So let's say this point represents my hinge, and this is my door. So we're going to label this here. This is a door. And we're going to label this as the hinge. Okay. And again, we're going to apply a load to the door. This is perpendicular, it's 10 pounds. All right. And, you know, most doors are roughly about 3 feet wide. So the width here of the door is 3 feet. Now, we're going to go ahead and label the hinge. We're going to call that point A. All right. Now, if you apply a force of 10 pounds to this door, and I ask you to calculate the moment about point A, you would simply say M sub A, that's a subscript A, that's the notation that you would see, is equal to 10 pounds. So 10 pounds times 3 feet. And it's causing what? Clockwise what? Clockwise rotation. So it's a negative here. So that's going to equal negative 30 pound feet. And we're going to drop that negative sign, but if you do, you must add the arrow. So it's going to be 30 pound feet going clockwise. Now, let me ask you a question which you can't answer because this is asynchronous, but if you could answer, if I was to apply a force that was on the side of the door here that intercepts point A, with this force, whatever it is, would it cause rotation? It wouldn't cause rotation because the line of action of this force, if you were to extend it, right, it would intersect the hinge. This force does not intersect the hinge, but this force would. And you can go and verify this. Go push on the door from the side. and see if it opens or moves. It's not going to move if you apply a force that intercepts the hinge. If you apply a force at any other angle, okay, now this is at a 0 degree angle, right? This force here is at a 0 degree angle. It intercepts the hinge. If you were to apply a force at any other angle, you would definitely have a moment, okay? So let's look at another possibility here. Okay, so again, this there's no moment. So the moment about A with this force is 0, okay? Because this is not going to produce a moment. Again, all you have to do is extend the line of action, and you see it's going to intercept that point. All right, let's take the same door. Let's take the same door here. There's the hinge. And this time I'm going to apply a force at a 45 degree angle. To the horizontal. And we'll say 10 pounds again here. All right, so here we go. We got a 10-pound force being applied right here. So that's a vector, right? And of course, the length of the width of the door is not changed. Still 3 feet. And the hinge is not moved, right? There's the hinge, point A. And if I was to ask you to calculate, the moment about point A here, you're gonna have to use your trig functions now. But again, this horizontal component, we're going to assume that the side of the door, the width of that is negligible here. It's not very thick. So we have a horizontal force here being applied. It's going to intersect point A. So we have f of x here, and we have fy. So let's find these forces first, though. F of x here is simply going to equal what? 10 cosine 45 degrees. Okay, and we were to find f of y. And by the way, this is, I'm not worried about the direction right now because even though this is going in the negative direction here, this component right here, the force, the horizontal component is going in the negative direction, and so is this one. But I'm not worried about that right now. I just want to know what the magnitude is of the force. Okay, the magnitude. So let's get out the calculator here. Okay. Morris is using his phone calculator, which is not the best. All right, so I have 45 cosine times 10. And this force is equal to 7.07 pounds. All right. And then if we try to find f of y, now I know this has direction, so we could just draw an arrow like this. That's the direction. Okay. Now f of y equals 10 sine 45 degrees, right? So 45 sine is the same as the cosine of 45 times 10. These should be the same, right? Because cosine and sine of 40, it's the only angle where the cosine and the sine is going to give you the same result. And that's complete. Now, as I said earlier, though, this horizontal force right here that you see is not going to cause any rotation. Okay, let's just assume that it's intersecting. It doesn't look like it here, but let's just assume it's intersecting point A. Okay, Let's assume that this is intersecting point A. But this force, F of y is not intersecting point A. So if we're going to calculate the moment about A here now, watch very carefully, it's going to equal the F of y. So it's going to be Fy times some distance, right? F of y times some distance. And so we know F of y is 7.07, right? Times 3 feet. And by the way, this is pounds. Sorry, I should have put the units there. And it's going, causing a clock, the vertical component of this vector of 10 pounds is causing a clockwise rotation. So therefore, this is going to equal negative 21.2 pound foot. 21.2 is negative, but you should write it this way. 21.2 pound foot, and it's going clockwise like this. Okay, so let's review one more time. We had to break this force up into its components, F of y and F of x. We notice that F of x, if you can move that force anywhere along this line of action, and it's going to intersect point A, okay? F of y does not intersect point A, it's actually going to cause rotation. So that's the way you think of it. Fy causes rotation, Fx doesn't. Okay, so we find the vertical component, which is 10 sine 45, which is 7.07. We put this in here for the force, times 3 feet. That's the width of the door. It's equal to 21.2 pounds. It's negative, so it's causing clockwise rotation. Okay. All right, let's keep moving here. You got a lot to do here today. Let's look at another example. Maybe some of you folks are mechanics and you've heard the word torque. You know, torque is another term for a moment. It's actually a moment, a torque is. So you've heard of a wrench, torque wrenches, and you've heard the term how much torque you're going to put on the head of the bolt or on the bolt itself. And we actually have an example in the book. This is example 3-4 I want to go over with you in the textbook. Okay, and it looks something like this. You have a square-headed bolt, and then you have a wrench, an open-end wrench. Like this. All right. Now, this is the center of the bolts right here, and this distance right here to the point on the wrench handle. This distance right here is 150 millimeters. Okay. And this distance right here is equal to 100 millimeters. Okay. And they have a force now that is not perpendicular to the wrench here. It's coming out like this. And they say this is 12. And this is 5. Okay. So this is a force triangle right here that you see, and the force being applied to the wrench is 52 newtons. So this force here obviously is not perpendicular to 100, and it's not perpendicular to 150, but the components of that force are. So we'll call this Fy, and we'll call this horizontal component, we'll call Fx. Okay, and we're going to call this point A. Point of rotation is A. So we want to tighten up this bolt. Okay. So how do we do this? This is a force triangle. You would have to use the Pythagorean theorem to calculate what the hypotenuse is, because sometimes it's not given. So use the Pythagorean theorem and you will find out that the hypotenuse here is 13. This is the force triangle. Okay. So let's break this force of 52 newtons into its x component and its y component. So F of y, okay, that's this force here, is going to equal the 52 newtons that you see here. Now, look at the force triangle and find the side of the triangle that parallels the force Fy. It's 5. But you're going to have to take 5 divided by the hypotenuse. So it's 5 divided by 13. All right, equals. And when you do the math here, you're going to get 20 newtons. Again, what I did is I took the side of the force triangle that was parallel to this leg, and you divide that by the hypotenuse, which is 13. So you're breaking up this force into its components. Now, this Fy is perpendicular to 100 millimeters. Now let's find f of x. F of x is equal to 52 newtons. Find the side of the triangle that parallels this is 12, divided by the hypotenuse, which is 13. And this is, when you do the math here, it's going to be equal 48 newtons. Okay, scoot that up a little bit. All right, so now we're going to take the moments about A. We have two, sorry, you can't see A now. We have two forces that are causing a moment about A. We have F of X and F of Y. F of Y is perpendicular to 100. F of X is perpendicular to the moment arm 150. So when we take the moments about A equals, so this Fx has a moment arm of 150 millimeters, and Fy has a moment arm of 100. So let's take Fy first. So Fy is 20 newtons. Okay, that's the unit for force in the SI system is newtons times 100 millimeters. Okay, now you can see that that's called Fy is causing a what? A clockwise rotation. So we're going to put a negative sign out here because it's causing clockwise rotation. This force here times 100 is causing a clockwise rotation about A. This force here times this moment arm is also causing a clockwise rotation about A. So minus here. Well, I'm going to go ahead and say plus, but then we'll put negative here. Okay, 48 newtons times this moment arm of what? 150. Okay, so you're going to get a negative 2,000 Newton times meters here, excuse me, Newton times millimeters minus 7,200 Newton times millimeters here. All right, so when you solve for this, you're going to get the moment about A is equal to negative 9,200 Newton times millimeter. But the way you should write this is this way. It's causing clockwise rotation that way. So this example is in your textbook, and I encourage you to look over it. And I also encourage you to try to understand how the force triangle works. And that was the reason why we did this problem. Okay. Now I'm going to do a problem in the back of the section here, back of the homework area. Look, hang on. I want to work problem 3-3 in your textbook, okay? And it looks something like this. Point A here. You have a force coming this way. Remember, a force is a vector, and this is 39 pounds. That's 39 pounds, not 391. That's 39 pounds. And they give us a force triangle here of 5 and 12. So if you do the Pythagorean theorem here, you know that what? The hypotenuse is 13. Right? So this is just simply pointing to the hypotenuse. All right. And then we have a 60-pound force here. And it gives us a distance of 20 inches here. And it gives us a distance of 32 inches here. All right. So we want to take moments about A. So we have to find the components for this force, and we only have a horizontal force here. So let's do this. So the moments about A equals the 60-pound force here times this moment arm of 20. See the distance, this force can be translated at this point anywhere along this, called the line of action. It can move anywhere on this line. This force can, but it's always going to be 20 inches from A, the perpendicular distance. Okay, so we have 60 pounds times 20 inches. And that's causing a counterclockwise rotation, so that's positive. Okay, I'll just put a plus. I'm not going to always do this, but for right now, I'm just going to show you this because it means this is causing a positive moment. It's moving counterclockwise. Now, we're going to have to find out what the horizontal and the vertical components are here. However, we don't have to worry about what the horizontal component here is. Here's why. If you were to move the horizontal force anywhere along this line of action, you will see that it intersects point A. So the horizontal force here, or the horizontal component, does not create a moment about A. The vertical force does. So F of Y does create a moment about A. It does. And Fy is going to be the force of 39 pounds, okay, times what's the leg that's parallel to that force? Is 12 divided by the hypotenuse, which is 13. All right, so that's going to be, we can do the math here. Let me get my calculator. So 39 times 12 equals divided by 13 equals 36 pounds. Okay. So Fy does contribute to the moment. F of X does not contribute to the moment. So once you break that force of 39 pounds up into its components, you realize Fx does not create a moment about A, but Fy does. So, and it's also causing a what? It's causing a counterclockwise rotation. Remember, counterclockwise is positive. So both of these forces are causing a counterclockwise rotation. So it's going to be plus, I'm going to put a little positive sign here. It's going to equal 36 pounds times 32 inches. Okay. And let's just check this. Okay, so we got 60 times 20. That's 1,200 pound inches. All right, plus 36 times 32 is 1,152 pound inches. They're both positive, so we add them together. A equals 2,352 pound inches. 2,352 pound inches would be the answer to this problem. Okay, so that's problem 3-3. Let's work problem 3-5 now. Okay, so hang on just 1 second. I'm gonna turn the paper here. Need that sheet. All right. So this is problem 3-5. So we have another cantilever beam out here this time. The point of connection is point A. And we have a force here of 800 pounds right there. We have another force coming in like this at an angle here. And there's a 3, 4, 5, right? The Pythagorean theorem was 3, 4, 5. And make this a little bit neater so you can see that that's a 5. And this is 200 pounds here. And then we have one, which is 400 pounds, which is perpendicular. So this 800-pound force is perpendicular to the cantilever beam. And this force of 400 pounds is also perpendicular to the cantilever beam. But this force here is not. We need to add our dimensions here. So this is 5 feet here. Okay. And then we have, this is 7 feet here. And this is 3 feet here. Okay, the distance from here to here is 3 feet. So the total length of this beam is 10 feet, right? All right, so we're going to take moments about A. Let's do this. Moments about A equals, all right, you got 800 pounds. Now, what is the distance from this point of the vector to point A? What is that distance? We got to do some math here. We've got 7 feet from here to here. And this is 5 feet to this point of application. So actually, this is going to be 2 feet here. okay? I know it's not drawn to scale, and I apologize for that, but that's 2 feet. So we're going to have a negative 800 pounds. And the reason I made it negative is because it's going clockwise. It's causing clockwise direction about A times 2 feet. Okay. Then we have this force being applied. Guess what? Here we have the same issue with the horizontal force is not going to contribute to the moment here because it's going to intersect point A if you were to extend it. So minus 200 pounds times, now we said that the horizontal component will not contribute, but the vertical component of the force will. That's this one. What is that force there? So it's going to be 200 pounds. What is the leg of the triangle that's parallel to that force? It's 4 divided by 5. You always divide by the hypotenuse times this moment arm of 7 feet. 7 feet plus, now this vector here, this 400-pound vector here is causing a counterclockwise, so it's positive. So we got a negative and a negative over here, but plus here, and you're going to have 400 pounds, right? Times 10 feet. So make sure did all that right. Now let's do some math here. Let's add all this up. So 800 times 2, you know, that's a negative 1,600 pound feet, right? Then you're going to have 200 here times 4 equals divided by 5 minus, now this is 1,600, all right? Let me go back to this one again. It's going to be 200 times 4 equals divided by 5 equals times 7 equals, and that's going to be minus 1,120 pound foot. Okay. Plus, you're going to add this last one now, plus 400 pounds times 10. So that's going to be a 4,000 pound foot. Okay. So a negative number, a negative and a positive. So we got negative, so 1,600, sorry, my calculator acting up, 1,600 plus 120, make that negative, plus 4,000 equals, so the result here, MA is equal to 1,280 pound feet, and it's going clockwise. Okay, so let me move that up a little bit. So here's, you should get into the habit of boxing in your final answers, so Mr. Morris doesn't have to go all over the place looking for it. Okay. All right, so you're not here to ask questions, and that's okay. I'm going to do one more problem here for a couple. Moments, and then we're going to get into couples. Okay, sorry. We're still working moments right now, and then we're going to do some couples. All right, so hang on just a second here. Find my lecture notes. All right, so here we go. So this is another problem, not from your textbook, but from a different textbook that I use sometimes. And I'm going to work through this one for you. I'm going to write down the problem statement. It says, determine the moment about point A of each of the three forces acting on the beam. All right, it says determine the moments about determine the moment about point A of each of the three forces acting on the beam. So let me draw the beam here. And you only need to realize that what we're drawing is actually called a free body diagram. We're going to get more into that a little bit later, but right now I have a cantilever beam here. All right, and we're going to come out. We're going to apply a force here. A little further, I'm going to apply a force here. Now this one is going to be a little bit trickier because this beam here has a slight angle to it here, or has it's like this L-shaped beam, right? So this force here, F1 is 375 pounds, okay? This force here, F2, we'll call that, is equal to 500 pounds. All right. This is a force triangle 3, 4, 5. Okay. Again, this is point A. Down here is going to be point B. All right. And we also have a force like this. Actually, it's coming off like this at an angle. So we're going to have a horizontal and a vertical component for that force. So this force here is 160 pounds. And this distance here, we need to know this distance is 0.5 feet. 0.5 feet. This angle here is 30 degrees. All right. So we will have to take this force of 160 pounds and break it up into its horizontal and vertical components. Now we need some dimensions here. This dimension here is 8 feet. This dimension here is 6 feet. And this dimension right here is 5 feet. Okay, how many forces are being applied to this beam? We have 1, 2, and 3. This is F3 here. F3. So let's take each force at a time. Let's just take F1 first, okay? So what is the moment? Here's how I'm going to do this. What is the moment about point A with force F1? I'm going to put this in the subscript as well. The moment about A, F1, is simply going to equal what? 375 pounds. And it's going in the clockwise direction, so it's negative, times 8 feet. You do the math here, you're going to get equals negative 3,000 pounds, pound-foot. Now, a kip is 1,000 pounds. So if you haven't heard of the term kip before, KIP, that means 1,000. So we can change pounds to kips. So that's going to equal 3 kips times feet. And it's negative, but I'm not going to put the negative sign over here. I'm going to show the direction, which is clockwise. Okay. Now, let's do the next one. Sorry. So that, again, let's review. F1 is 375 pounds times this distance from point A, because that's what we're taking a moment. It's about point A. It's 8 feet. So we multiply these two numbers together. It's negative because it's going clockwise. It's causing a clockwise rotation about A. And it's negative 3,000 pounds. And so we convert that to kips. A kip is equal to 1,000 pounds. And a ton is equal to 2,000 pounds. But a kip is half of a ton. So times feet, and it's going clockwise. So you get rid of the negative sign and you change the rotation here to clockwise. Now let's do the other one. The moment about A with respect to F2. Well, if you look at force F2, which is 500 pounds, the point of application is at an angle. And the force triangle is 3, 4, 5. Notice the horizontal component here is not going to contribute to rotation about A. The horizontal component is going to intersect A. So you need the vertical component of this force. So it's simply going, and it's going to be this 500 pounds. What is the leg that is parallel to the vertical component is 4 divided by 5, right? Times this moment arm, you have to add the 8 and the 6 together to get this moment arm. So it's 14 feet. Okay, and it's going to be negative because it's causing clockwise rotation. So MA, the moment around A with respect to F2 equals negative 500 times 4 or 5 times 14. When you add all this together, you're going to get a negative, this equals a negative 5,600 pound feet. Okay, so this is going to equal 5.6 kips feet. Again, it's going this way. Now the last one, see if I can get my camera right here. Sorry about that. F3 down here is 160. We have to break it up into its components first. And both of the components contribute to the moment about this point A. Let's take this very slowly. Let's first find the, we're going to take 160 pounds, right? And to get this vertical component here, we're going to take 160 cosine of 30. So the moment about A with respect to F3, moment about A with respect to F equals 160. Now, you see this, we're gonna break it up into its components, this one and this one. So it's going to equal 160 right here. This force here is causing it what clockwise, so it's negative 160 pounds times the cosine of 30. Okay, times this moment arm of 8 plus 6 is 14 plus 5 more makes 19 times 19 feet. All right, plus now look here. This is interesting, but the horizontal component now of this force, which by the way is going to be 160 sine of 30, it does not use this moment arm. It uses a moment arm of 0.5. See the distance from here to here. You know, if you were to extend this back along this line of action here, this force here is 0.5 from A. So watch how we do this, okay? So it's going to be plus, because it's causing counterclockwise rotation. So this force here is causing a counterclockwise rotation about A. So it's going to be 160 pounds times the sine of 30 degrees times 0.5 feet, okay? And when you do this, you're going to get equals a negative 2,593 pound-foot, which is equal to a negative 2.59. Okay. Hip foot. Okay, it's hard to write here. It's a negative 2.59 kips times, it's not divided by feet, but times feet. And so this is the final answer. You're going to get rid of the negative sign, 2.59 kip feet. And your sign is going this way. I do have one more moment problem to do, and then that will be it for the moments right now. So let's do that. And then we're going to do couples. All right, so this is another problem from a different textbook. And you have a free body diagram or beam that looks like this. Okay, this is point A here. And you have a force that comes down like this. And you have a force like this. And by the way, this force here, called F1, this one here, F1, equals 250 newtons. And the angle that it makes right here, this angle is 30 degrees, 30 degrees. And the distance is from point A is 2 meters. Okay. So we have the force is 250 newtons. We have the angle that it makes with the vertical, which is 30 degrees. And we know how far away it is from point A. Then we have another force over here, F2, is equal to 300 newtons. Okay, and this distance here is 3 meters. And it's at 60 degrees. 60 degrees here. Then we have another force being applied down here. And this force is 500 newtons. That's equal to F3. So 3 forces, right? And the distance here is 4 meters. And down here, they give us a force triangle here. This is 4, 3, so you know that's 5. So let's take the moments about A, and this is, we just want to take moments about A with each force, okay? So let's take the first one. So the moment of A with respect to F1 is simply going to equal 250 newtons times the cosine of 30 degrees. That's going to give us this component here times its distance from A is 2 meters. Now, if we were live, I would ask you a question: how come the horizontal component doesn't contribute to the moment? Well, you can see that it's on this line and it's intersecting point A. So it does, the horizontal component does not contribute to the moment. So it's negative, it's going, this component here would cause clockwise direction here like this. So it's negative. So we're going to get, see if I got this written out correctly. I do. That's going to equal negative 433 Newton times meter, or you should write it out like this: 4.33 Newton times meter clockwise, like that. Okay. Let's look at this next force here. It's going to be kind of hard to see here, but again, the horizontal component of this force is not going to create a moment about A. So only this vertical component will. The horizontal component will not contribute to the force, or the moment rather. So here we're going to have the moment about A with respect to F2. It's just simply going to equal 300 newtons times the sine of 60 degrees times this distance here of 5 meters. Okay, I hope you can see that. I'll have to move it up and down now because it's taking up most of the page, but the moment about A with respect to force F2 is the 300 newtons, sine of 60, that gives us the vertical component. It's also still causing a clockwise rotation, so it's negative. So this is equal to negative 1,299 Newton times meter. And we're just going to change that to 1,299 Newton times meter clockwise. All right, if it's okay with you, I'm going to come up here and do the last one because it's kind of hard to see the paper. Try to zoom out some. That will help a little bit maybe, but I think I'm just going to make a situation worse. So I'm going to come up here to solve for this one here. All right, so this is going to be the moment about A with respect to F3. The moment about A with respect to F3, you got this 500. Both of these components contribute to the moment, both of them. The horizontal component does, and the vertical component. However, one is clockwise and one is counterclockwise. So I'm going to do the clockwise. The vertical component of this force can cause a clockwise rotation about A. The horizontal component of this force causes a counterclockwise rotation about A. So this is simply going to equal, the vertical one is going to be negative 500 newtons. Okay, again, because it's going in a clockwise direction, times, all right, so this is the force that's causing the rotation, Fy, if you will. So it's negative 500 times 4/5. Remember, because the 4 is parallel to that force. Okay, times its moment arm of 5 meters. Okay, 5 meters. So that one, now though, we have to add this one to it. So it's going to be plus 500 newtons times 3/5 times, now its moment arm is right here from A. The moment arm here is perpendicular to 4 meters. So 4 meters is written this way, and it's going to equal to negative 8,000 newtons times meter. And we're going to just, actually it's not 8,000, sorry, it's 800. Sorry about that. It's 800 newton times. Let me check that on the calculators to make sure that that solution is right. These are the numbers I got earlier. So we're going to have 500 times 4 equals 5 equals times 5, negative 200, okay. And then 500 times 3 equals divided by 5 equals times 4, and then minus see here. I'm going to check all these just to double check everything. So this first one we did earlier, we have 30 cosine times 250 equals times 2 equals negative 430. That's correct. Okay. And then this one we got 60 sine times 300 equals times 5 equals, and this is correct. So I'm just checking the last one. I think I did something wrong here. I'm just double checking. 500 times 4/5 times 5. All right, so 500 times 4 equals divided by 5 equals times 5. Negative 2,000, and then 500 times 3 equals divided by 5 equals times 4 equals. So I got a positive 1,200 minus 2,000, and I got negative 800. So that is correct. So the moment about A with respect to F3 is a minus 800 Newton times meter. Okay, so that's going to complete, I don't know if you can see that, but that's going to complete that problem there. And we are finished now with moments. Now I want to start couples. And we got several problems to do here. And I think the best thing to do is actually create a separate video for couples. So I'm going to stop this video right now, and I'll post it. And we'll see you soon.